Okay, the recording started. I'm going to wait a few seconds to get started.
Yeah, sure.
We'll let a few more people finish joining. Okay, why don't we start? Welcome everyone to the Air Sea Fluxus from Space webinar series run by Oasis. Today we have Louise Nuijens from the Technical University Delft, who's going to talk about clouds as momentum pumps for the ocean. And I'll let you take it away, Louise.
Thank you, Sarah, and thank you for inviting me. This is my first. I'm going to take this webinar as an opportunity to talk a bit more generally about things that I'm working on with my group, Eduardo Jacot, in collaboration with Paco Lopez Decker, who many of you know. Also, Chris Chapman from CSRO, who was on a sabbatical at TU Delft. And I'm an atmospheric scientist, and I think many people who are here might have more of an ocean background. So I'm going to try to explain a bit slowly, I hope, how clouds may act as momentum pumps for the ocean. And this is a project that we're working on, and it's an idea, an hypothesis. And as I'm explaining it, I'm guessing some of you who've worked on air-sea fluxes will say, well, we've known this all along because there's gustiness introduced by convective clouds. And but there's more details to it, and I'm hope to give you some more insight on that. And I'm going to start with just showing you a picture of the atmospheric boundary layer. Here I'm showing you the typical U-shaped profile of the wind. And I work on cloudy boundary layers, which means the ocean surface is warm enough to drive convection. And so you have dry convection sitting above the sea surface. Um, at the top, you have the mixed layer height, which corresponds often with cloud base. And above that, you have a cloudy layer. And this means that the way I see the boundary layer is typically as sitting above the mixed layer, as you are starting to mix over a somewhat deeper layer than just below cloud bases. Now, ways in which the presence of clouds can change the winds can happen in a number of ways. Um, First of all, and this is something that I've worked on in the last 5 years, is whenever you have moist convection and you have convective updraft, compensating downdrafts, it means you're changing the wind profile a little bit higher up in the atmosphere. And this will matter for the surface because you get turbulent entrainment across the mixed layer top. And you have dry convection, which then communicates the wind that you will have at the mixed layer height towards the surface. So in a longer term mean wind balance, what the profile of wind is higher above will matter for the surface. We also see that in the presence of clouds, the dry convective overturning in the mixed layer tends to be it's stronger. This can then also change winds down to the surface, where it gets communicated through smaller scale turbulence in the surface layer. And of course, when clouds start to precipitate, you get very strong downdrafts, which then drive gust fronts and can also change winds directly. So all of these different flows, depending on the scales that you're looking at, do things to winds. In fact, yeah, the wind is all these different flows, and you can see these different flows very nicely when you look at cloud fields. So if you look at the subtropical North Atlantic, this spans about 3,000 kilometers. You see lots of different patterns of clouds that indicate the different flows that are sitting underneath that in the boundary layer, from shallow convection, isolated little popcorn cumulus clouds to precipitating convection. And you'll recognize that by somewhat larger arcs of clouds sitting here along cold pool areas where you don't have any clouds, where convection is suppressed, to even larger mesoscale systems that are still shallow. This is not deep convection. This is convection with tops maybe near 2-3 kilometers. They tend to rain, and they're coupled to larger scale patterns in divergence. And we know that these patterns can be felt all the way down to the surface, because if you look at SAR imagery, you'll see that lots of these little cells of subcloud layer overturning, which means you have a little stronger wind, a little weaker wind. You see that in the roughness that is measured by synthetic aperture radar. Similarly, for cold pools, you get large structures, and I'll show some more of that later. So some of the questions we work on, thinking of how wind is really dynamic at the mesoscales and submesoscales, is, well, how does convection transport momentum, and how should we model that? Does it influence circulations that are really important for climate? And the question that I'll talk a bit more on here is, how does convection influence winds all the way down to the surface, and the wind stress, in particular in regions that don't have a lot of ocean activity, no strong ocean currents or eddies. And a little bit more about my motivation of why we're looking at this is, we know that global models have persistent wind biases near the surface. In particular, I'm working with people at ECMWF, and the IFS model, we know that there is an excessive bias in the wind direction, where the model produces too strong easterly winds, and particular under more unstable boundary layers. So this means there's either something wrong in the way we parameterize convection, in how we parameterize turbulence, or how we model wind stress, and it's a difficult coupled problem. Another motivation is that the way you're mixing convection and what that does to the wind is important for how mesoscale cloud and circulation patterns build up. So in some work that we recently did looking at a mesoscale model, we can play with not having any momentum mixing by convection, or not having any parameterized shallow convection at all, which is also effective at mixing. You'll see changes in the eddy kinetic energy that you're producing, where without all of that mixing, you're enhancing variance of wind, eddy kinetic energy on mesoscales, and you start to change not just the circulation patterns, but also the cloud field statistics, the number and the sizes of clouds. And this again is important for cloud radiative effects and for climate. And in the last years, I've become motivated by a lot of work that the ocean community has been doing, looking at how winds in the atmosphere are driven strongly by SST patterns and currents. I'm guessing you're familiar with these type of pictures showing SSTs in the Gulf Stream. This is from icon simulations done at 1 kilometer. Underneath this is, of course, a rich ocean vorticity field. And in work also that will be shown in the next couple of webinars by others in Europe, by Agostino, by Lorenzo, these patterns have strong impacts on winds. And so I'm coming from the other side and thinking, well, I'm interested in this warm soup in the subtropics and the tropics, where the ocean is maybe less active, but where the atmosphere dynamics revealed by those cloud patterns are playing a rich role. And so I'm motivated to understand what that does to the ocean, and to what extent it's influenced by the ocean, or it works the other way around. And so I like to look at patterns of wind over warm oceans, and I can zoom in, and if you would squeeze your eyes, you see all these little pockets of cells, which we know are related to convection. in the simulation, and I'm trying to understand what does that do to the mean wind, what does it do to surface wind stress. And I'm going to show you some of the work that we're doing on how it influences wind in three different ways. And let's see if I get to all of these. One way to look at wind stress and the influence of convection is if we can derive it from the observed momentum budget in the atmosphere. And that's something that we did using field observations during Eureka campaign in 2020, kind of reviving some of the seminal work that was done in the 70s from one of the first ocean atmosphere campaigns. I can also look at wind stress from atmospheric large eddy simulations, really simulating it down to 100-meter scales. And I'm going to do that making use of cloud botany, which is a large ensemble of simulations that has been done in these conditions of the trades of the subtropics. And finally, if I get to it, I'd like to show you a little bit something of how we look at winds from shipborne wind lidar cruising the ITZ in a field campaign that took place last summer. And all of these are efforts where a lot of other people have worked to collect the observations and do the simulations. And I'm really grateful for being able to contribute and use these. So I want to start with this first question, looking at how we can derive wind stress from the observed momentum budget, because that led, at least for me, to some insights that motivated also looking more closely at mesoscale wind patterns. So in this picture that I showed you at the very beginning, ultimately what I'm trying to understand is what sets the eddy momentum fluxes. And typically what we solve in a model is some sort of filtered Navier-Stokes equation where you look at the tendency of, for instance, here, the mean zonal wind that is influenced by a large-scale forcing, horizontal and vertical advection of wind, the geostrophic wind, Coriolis pressure gradients, and that part which introduces the nonlinear advection terms or the eddy flux divergence, where if we typically assume that there's horizontal homogeneity, you only look at the vertical divergence of these eddy fluxes. And the eddy fluxes we can sort of split up into a term that might be smaller scale, shear-driven turbulence, and a part that's driven by convection or buoyancy-driven flows. And what people did in the BOMIX campaign was look at arrays from radiosonde balloons that they would launch from an array from ships. And when you work in that array, you can get profiles of winds, pressure, everything you need to obtain your large-scale forcing and your tendency over many, many days. And in Eureka, we could do something similar, but not from radiosondes launched from a ship array, but from an aircraft flying circles, dropping sondes. And here's a picture of Guy George, who's now my office mate, who worked on dropping all of these sondes on 13 of these flights, which lasted 8 hours each, where you would collect many profiles. And Guy has done work showing that when you do these kind of measurements, you can obtain very realistic estimates of the large-scale forcing in particular, what's really difficult, of the large-scale divergence. So from Eureka, they had these different flights, 8 hours long on different days, about 13 days, and there were many different circles. And here is a picture of the mean divergence and the variability in divergence over the course of the campaign, showing you that there were days with sort of mean mesoscale ascent and mean mesoscale descent. And Guy has shown that you get these strong mesoscale patterns. Now, I'm just using that to constrain the large-scale budget. In particular, what I do is I take all these forcings and I construct the mean budget over this whole period, and then look at this term, the eddy flux divergence. And if I have that tendency, I have to assume something about where these momentum fluxes may vanish. For instance, at the top of the boundary layer. And then you can integrate down and get the momentum flux that you would get at the surface. And so this is a profile that shows you the total momentum flux down to the surface, where you would come up with a near surface stress that will be on average something like 0.1, which is very similar to the mean stress that was measured with the in situ sail drone that was measuring across these different days during the campaign. So we have some validation that what we're doing with the budget is actually getting us something that is realistic. We also had aircraft measurements and drone measurements. This was the Q Raven from Colorado. Gijs de Boer was operating that. The ATRs from the French. They also measured these fluxes, so we get some validation there. Now, what we're interested in is look at what is actually the momentum budget that you get at the surface. And again, to show you a little bit of a picture of what you might expect, this is a typical textbook picture of the momentum balance that you have. Here you're in the subtropics, so maybe up here you get your Azores high, and here you get the ITCZ and your low pressure. So you have your pressure sloping something like this on average. So you have a pressure gradient here towards the southwest. And in everything that I'm showing, I'm using a natural coordinate system. So everywhere I'm looking into the direction of the flow. And the perpendicular, the normal line is defined as positive towards the left of this. Now, the typical textbook flow that you'd expect is if your pressure gradient is in this direction, your flow would be across your isobars towards low pressure. You get a Coriolis forcing that acts towards the right of the flow, and you get a frictional force that is acting opposing your mean wind. Now, during Eureka, on average, that momentum budget, we observe something very similar, except for one difference, which is that the residual tendency, your eddy flux divergence term, your friction near the surface is not actually opposing the mean flow, it's sitting at an angle, which means that there are contributions to this term in the crosswind direction, where if this is negative, this means that there's actually a contribution that is tending to pull the flow towards clockwise, a veering of the flow. The other way would be a backing of the flow. Now this is the mean budget, and it's interesting to look at different days. So here again on the left, I'm showing you that mean budget, and you can look at individual days, and then you find there's a lot of variability. On some days, here on January 28th, we had weaker winds, and you actually find something where the wind is actually almost across isobars. And you find a frictional component that's actually suggesting that what all the eddy momentum fluxes are doing, they are tending to back the wind, which is maybe what you expect a frictional term to do. But there are other days, especially as the winds were strengthening and as convection was getting more vigorous, you see that you're developing flow that's almost parallel to the isobars, where you get a much stronger component of this friction that is acting towards the right of the flow. Now, if you want to see an example of what the cloud field looked like on this day, on the left here, you see a day where there were very weak winds, and you see just more of this powdered sugar, very small clouds. Whereas on the more vigorous convection days, you actually see much larger mesoscale structures. Um, so what we were learning, and we analyzed a lot of the LES simulations that were done, more realistic hindcast during the whole Eureka period. What you see is in LES, if you split up the tendencies into those components that are driven by smaller scale turbulence and convection, you see that this F, this frictional term, is actually the contribution of small scale turbulence that does act opposing the mean flow, and convective flows that act to accelerate and to veer the wind. So important that we learn is that the bulk effect of the convection flows is to really change the momentum balance and to change the direction of the stress vector. Now, I showed you this where I derived what the actual near surface stress would be if I would integrate along this profile of eddy flux divergence. If I do this on individual days and derive what the surface stress would be, you start to see that I'm getting estimates that are very different from what is suggested from the in situ measurements. Now, this doesn't mean that that frictional tendency is wrong. It means that I'm making an assumption that's probably not valid, which is that you have large heterogeneity on mesoscales, which means that I cannot ignore that there are divergences of horizontal, that there is important horizontal divergence of eddy fluxes, which we always assume we can ignore if the flow is homogeneous. But in the presence of this rich mesoscale structure, we cannot do that. And we actually observe that these scales between 2 kilometers and 20 kilometers have large contributions to momentum fluxes. Okay, so a short summary of what we learned, which is that the variability in wind is really rich at these scales. We also see that as you strengthen the wind, we know that convective organization gets stronger, you get larger cloud systems. This happens because stronger winds drive more latent heat flux, which tends to create deeper moist layers, more latent heating, which can reinforce circulations. You get precipitation, which drives flows. And that these flows apparently do something to the direction of the surface wind stress. And also that we probably cannot ignore horizontal divergence of eddy fluxes. And so questions that I cannot answer from these type of measurements is, well, does convection actually generate a meaningful momentum flux all the way down to the surface? Or does it merely change the wind speed and then the small scale turbulence picks up? So these are questions we're trying to address with all these large eddy simulations. Now, before I show you something on that, a little something on this point. Convection drives variability in wind at these scales. One of the ways we can use these large eddy simulations is if we have simulations of down to scales of 100 meters, we can feed them and derive what would be the wind stress or latent heat flux that you would model through a core-like algorithm. And we can ask which scale of variability actually matters for driving the overall momentum flux. And that's something that Chris Chapman was working on when he was visiting us. He was doing one type of 100 kilometer by 100 kilometer simulation of shallow convection. Here you see latent heat flux on the left and wind stress. In the dark here, there's liquid and rainwater paths. So that shows you when there's clouds developing. And you see initially when the simulations spin up, there's no clouds yet. And you see that as the dry convection intensifies and starts to become cellular, you start to see clouds appearing. You see differences in wind speed on the order of several 5 meters per second. associated with that on small distances, variations in latent heat flux on the order of hundreds watts per square meter. And you start to see patterns of wind stress. And as your convection starts to develop into lines and clusters, you start to see cold pools developing. It starts to rain. You see much larger variability in all of these fields, where you drive strong divergence in wind near the surface. You drive stronger wind stress. You drive large differences in latent heat flux. So what he did is taking these type of simulations and use the output of the first model level at a few meters above the surface and feed them into an offline core algorithm. We do that because we in our simulations probably don't use the most latest version of core. And then he can play with different filter scales and look at contributions to that stress. So what you see on the top right is on a somewhat different scale here is one snapshot of the surface wind stress along some of these cold pools. You see them developing here. And then what he did is he basically just took the core algorithm and modeled as if you have all these little buoys sitting in the domain and you average over 10 minutes. And then you say, well, what if I would see only a wind speed or a smoothed field where I remove all scales smaller than, say, 2.5 kilometers. So what this field here is showing is the perturbation, the difference in the true wind stress and the wind stress that you'd see from a low pass filtered field, where here you only give it scales longer than 2.5 kilometers. And then you see some of the difference here appearing, especially in these lines of the cold pools. And especially for the filter scale of 25 kilometers, you see that you're recovering most of your stress field, which tells you that these scales between 20 kilometers are really important for adding to stress. And if you give it a 25 kilometer smoothed wind field, it will miss all these contributions. Even larger scales than 25 kilometers don't add very much. Here you see if you get 100 kilometers, you don't see big changes. Now, in some of these regions, these differences will be really large. You also see that the field overall starts to show up as a bit of orange here, which tells you that all those little convective-driven cells, the small perturbations in wind speed that you're having there, even those will add non-linearly to stress that are important for generating mean wind stress, and gives you a sense of that these small scales matter for setting your overall mean wind stress. So he's working on quantifying that in more detail. The picture for latent heat flux looks very similar, right? These scales between 2.5 kilometers and 25 kilometers are very important. And it's not only these areas where you see stronger perturbations in the wind field, but also across the domain in the little convective cells, you add perturbations that add to the total latent heat flux. So these simulations are part of a broader set of LAS simulations. There are 103 of them, so they're called cloud botany. They're run on 150 by 150 kilometers with horizontal resolutions of 100 meters. And they're semi-idealized in that they don't use direct observed forcing or forcing from reanalysis, but they prescribe conditions that we know are typical for the trades and slightly different combinations of them. So, for instance, slightly different wind speeds, different surface temperatures, differences in temperature lapse rate or mixed layer humidity, or how quickly humidity falls off with height, and differences in the large-scale divergence. And these different combinations give you lots of different patterns of wind and lots of different patterns of clouds. And we're using these to look at this question of what's the actual momentum flux that convection produces down to the surface versus perhaps even smaller scale flows. And one of the things that is key is that we're starting to learn is where convection really matters the most is in driving the horizontal covariances in the flux, which then have an effect on the mean wind, perhaps even more so than the covariance between a horizontal wind perturbation and a vertical wind perturbation. What you see here is the whole ensemble presented as a function of the wind speeds that develop. And what you see here is the resolved wind variance. And the little dots show you the mean over the domain. Actually, they're the fluxes that are determined over a scale of 20 kilometers. So perturbations are taken with respect to a 20-kilometer mean. And they're colored by how much they rain. So that tells you something about how vigorous the convection is. And so what you're seeing generally is that if you're running simulations with increasing wind speed, they'll develop different wind speeds near the surface depending on their organization. Generally, the variance will go up with wind speed, which is what you would expect because stronger winds also mean stronger wind shear down to the surface, which helps your variance grow. You see some examples of runs that rain very little here on the left, more sugar type of convection. Down here, a simulation that rains more, which is organized in streets, and here where you get cellular cold pool convection. Especially when the runs start to rain here in blue, when they produce more than what's the average amount of precipitation, you see all of these simulations jumping up in the amount of horizontal wind variance that they're producing. And this is the first model level, 7 meters above the surface. This is what these fields look like. This is for one of the low wind speed cases, 5 meters per second. On the left, you see the wind field. On the right, you see the vertical velocity perturbations. And now this partly helps show us why convection is not very efficient with carrying momentum flux all the way down to the surface. Because while you're getting increasingly large scales of your horizontal wind perturbations, your vertical velocity perturbations are still quite finite and confined to small regions. So for instance, here you have this cold pool and you have this large area with very strong winds. Within that area, you actually have very little vertical velocity because your convection is strongly suppressed. Only where you're having strong convection is right here at these boundaries of the cold pools. And in the areas where the rain is coming down, which in this case is always quite in the center of these cold pools. So if you look at what's the actual resolved eddy momentum flux that you're getting, you start to resolve something that looks like the Dutch and the French flag, all these red, white, blues. This is the zonal momentum flux, and this is the meridional momentum flux. The momentum flux really changes in sign from negatives to positives to negatives to positives, which means that if you average over a region of maybe 20 by 20 kilometer, overall, these fluxes don't do very much to the mean wind. They're just fluxing wind around without changing it. And that's what you would expect for circulations that are perfectly symmetric. Now, when can you actually start to flux stronger momentum? That's when you have stronger winds and your circulations start to become more asymmetric. And you start to see this in cold pools that are driven under stronger winds, where you start to get these little squall lines, where you get most of your rain actually trailing just behind where you have your updraft area, and it starts to interact with the flow in a way that's where you drive most of your fluxes for both the zonal and the meridional wind. Now, what we're trying to do, because this is very much ongoing work, is trying to look at how this compares to a very big component, which is the still unresolved turbulent stresses. It scales less than 100 meters. And what you'll find is both at low wind speeds and at strong wind speeds, the resolved momentum flux is really still only 10% of the total flux, and the other 90 is from very small scale stresses, which tells you that the way that convection helps drive momentum transfer is mainly by driving a lot of that larger wind variance, the covariances between the horizontal wind components. So that's what this picture is trying to show. It shows you the mean zonal and meridional momentum fluxes as a function of wind speed. Of course, you see as the wind speed goes up, you see that convection can carry more momentum flux. You also start to see, especially in the crosswind component, that you get a lot more variability in time when it rains at the stronger wind speeds. But at stronger wind speeds, you also have very much more shear-driven stress. So here the contribution is only on average 5%. At low wind speeds, you can make a somewhat bigger contribution. If you drive cold pools, can maybe be 10% of the total flux. But a lot of that too depends on what's the scale over which I try to address what the mean flux is. If I calculate it with respect to a 20-kilometer domain, and I look across this whole 150-kilometer area, there's lots of areas where you don't have cold pools. So overall here, all the stress, shear-driven stresses dominate. If I go and I sit within a cold pool, and sometimes these can get very large, your subgrid might become quite small, especially as you are creating very stable conditions. And then the result can be a bigger component. So this is also something we're trying to get more quantitative about. Overall, the big question, which is something I'd also like to ask this community, is what are the scales of wind stress the ocean really cares about? And in our project, we're trying to learn more from SAR images about these structures that you see imprinted on the surface to try to see what happens with roughness of the ocean. What are the scales that you find, and are our large eddy simulations producing accurate surface roughness? At which scales should we apply a bulk core algorithm, which is designed to give you a mean stress over something like 30 minutes, which might be about 20 kilometers at a 10-meter wind speed. So these are open questions. So I have about 20 minutes left. I was going to try to sort of, without giving very strong conclusions, because it's a lot of work in progress, but in this picture that I was drawing at the beginning of how clouds act as momentum pumps, what you'll find is even the convective scale variability in these overturning circulations, small wind, weak wind, you see that it changes the surface roughness. Probably it changes little to the mean wind. Where the clouds rain, where they develop larger scale horizontal wind variance, that's probably where they start to change the stress. But this is something that we're working on. Something a little bit different is, and what's interesting about the wind is looking in regions that have very low wind speed. And those are regions that we captured when we cruised along the ITCZ all the way from Cape Verde towards Barbados in this boat-time ship campaign that took place last summer. And here we traversed across the ITCC, and some of the areas had really weak winds, some had stronger winds. And on the ship, we carried a scanning wind lidar. We put it on a stabilized platform in collaboration with Boris Conan from Nantes. And we were trying to do different types of wind measurements aimed to resolve the patterns of convective scale wind variability, as well as capture the vertical wind profiles. And by taking the full 40 days of cruise, I was trying to understand how the wind mixing develops with stability. And there's a result that I don't understand and that I also want to communicate to you, because maybe some of you will have insights. But what I'm showing you here are composites of wind. Here I'm showing you wind speed as a function of local time. So I'm showing you the journal cycle of the winds. This is a category where you find quite strong winds. And the different colors here show you winds measured at different heights in the mixed layer. So from darkest green, winds in the lowest 50 to 250 meters of the atmosphere. Below that, you cannot measure the wind with the wind lidar, so you can take another wind measurement with the sonic at 35 meters. So essentially what you're doing here, from the dashed line to the light green, you're moving up in the mixed layer. And you see that the winds are increasing, just like you would expect with your typical U-shaped wind profile. You see some of this journality here that also Jack was talking about last week or 2 weeks ago. And what you see here below was on the ship, the temperature that was measured, the temperature of the air and the temperature of the SST and the subskin SST. So here in this regime, I'm looking at cases that are unstable, where the air is more than 1 Kelvin colder than the SST. And in this case, where you have strong winds, you'll find that the ocean is well mixed in the most upper layers. Now, what's interesting is let's move to somewhat weaker winds between 5 to 8 meters per second. Here again, you see a little bit of a journal worm layer developing. And you also see that as you start to develop a journal worm layer, that there's this little dip here, but let's not overinterpret that. You start to see the winds are collapsing a little bit more onto each other because there's less wind shear. It's easier to maintain a better mixed wind profile. And now the most interesting result that I don't fully understand is what happens at the even weaker wind speeds, where you see a much stronger journal worm layer, which means that during the day you start mixing. So you see that as the profiles are separated, as winds are different at different height levels, at nighttime, during the day, you effectively start to mix and collapse these. But what's most interesting is that the shear here is the other way around than I would expect. So here, in fact, you have most of the day, you have the strongest wind speeds near the surface, and you have the winds decreasing as you go up. And then as you start to mix across the different height levels, and you start to effectively lower wind speeds also at the surface. Now, what I don't understand is what sets that negative shear, where different hypotheses have been offered. Is this some influence of swell that can generate stronger winds near the surface? This is a region of deep convection, so there should be swell, but here we're sitting at heights 50 meters above the surface. I'm not sure if that's still influenced by waves. Another hypothesis is that these are substantially different pressure gradients, but this is a composite over lots of different areas across the low wind speed ITCC regime. And so the working hypothesis I have right now is that in this case, you get this almost like a stable kind of boundary layer where your lowest surface layers are decoupled from the atmosphere above. And you are developing kind of very low level jet, which feels very little stress at the surface and is also not mixing with winds aloft. But I'm happy to hear your thoughts on this. And I also looked at this in a somewhat slightly weaker unstable composite, where you don't see these journal warm layers as strong. You see the similar signal developing. So that's sort of my last slide, a little something result that's recent that I don't understand. So I'm leaving you with lots of questions, but hopefully some insights what it is that we're working on. And I'm happy to take questions from your side for these last 15 minutes.
Well, thank you so much, Louise. Questions from the audience? This was really interesting.
I know
While
that
people are thinking of questions, can I just ask about the composites you just showed?
Yeah.
Those are composites over how much data? How?
So it's about 40 days of campaign, and I'm getting wind profiles basically every 10 minutes. So I'm just putting all of those wind profiles into 3 hourly bins, regardless of where they were measured. But just compositing them by then hour of local hour and by background wind speed, mean wind speed.
So if you were to assign uncertainties, it sounds like they'd be pretty small.
Yeah. So one of the things we're trying to do, or that's what I'm collaborating with William Broeg. I don't know if he's here. He sits at CNRS and he's interested in SWOT and SAR images of roughness. And we also made scans, RHI and PPI scans, all the way down to the surface. So we can actually work also to try to reconstruct even winds closer down to the surface to see if that signal holds. So that's the first thing that I would do. But otherwise, I find it still quite puzzling.
Yeah. There's a question in the chat from Shikar, right? Do you want to ask your question, Shikar?
Yeah.
Hi,
Okay.
yeah, I was just wondering if that could be because of the ocean current you're measuring in the tropical part where the ocean current may be, especially during the low winds, it could be as comparable to the atmospheric winds. I don't know. I was just thinking if that could like.
Yeah, so I also don't know, but this is, I think, also one hypothesis that maybe it's the ocean then adding momentum to the atmosphere. And I think when we will look at scans that we made all the way down to the surface, hopefully this gives us some more insight into whether that might be the case. We also had an X-band radar on the ship, so from those maybe we can reconstruct some of the currents and see if that will be the case.
I have another question. So you saw that there is significant variabilities in very small scales. Uh, Considering that the ocean is slow, but the atmosphere is fast, do you think that these small scale variabilities would be kind of like diffusive processes for the ocean while not for the atmosphere? And then we may have to uh, have different parameterizations for the wind stress for ocean and different for the atmosphere when we do that?
Yeah, so an open question to me is I don't know at what scales the ocean will feel this wind stress. Indeed, when the wind speed is fast, it will move over the ocean, and the question is if that variability leaves an imprint. At the same time, I'm a little bit motivated by thinking that it might, just from the first couple of LESs that Peter Sullivan has done, where he shows that even these small scale coherent structures in the atmosphere imprint themselves on the upper ocean flows and SSTs. I also watched work by what's his name? Um, Sid Almond, who
Hmm.
defended his PhD thesis with well, the ocean, you guys
You
know more.
you
I mean,
messed up not, yeah.
I was intrigued by the variability he showed in the journality of SST across like small distances or tens of kilometers, where you see large differences in the journality of ocean temperature. And he tried to attribute that to differences, right, in heat fluxes, in wind, in rain, in salinity. So I see some evidence emerging that even across these tens of kilometers, that the ocean in some regions seems to sustain gradients. But I think it's still an open question. Where it matters on a sort of larger scale is that the small scale variability in the atmosphere will, of course, have an effect on what the mean wind is that develops as this air mass moves. So on a somewhat larger scale, this will set the budget of the wind, where it can then, have an impact on the ocean.
Thank you.
I see Megan Cronin has her hand up.
Yeah. Yeah, great. That was super interesting. Okay, I'm an oceanographer, so
Yeah.
it's probably a stupid question, but um, if you were going to do like a layered budget analysis, I mean, obviously, if you have all of those shears and gradients, then it maybe doesn't make sense to do a layered analysis of our budget analysis for the atmospheric boundary layer. But could it be that the layer is just really thin? And I mean, in general, what would be the height that you would integrate to? Do you understand what I'm saying? I mean, when you were doing your momentum balance, it was all level. You were not integrating in height. But if you were going to integrate in height to look at like a box model of the atmosphere, what height would you integrate to? And in the case of you were showing in the last slides, would it be like meters? I don't know. What makes sense?
Right. So for the trades, the frictional layer, or the layer over which you have fluxes before they disappear, that's about 1.5 kilometers.
Uh-huh.
Um, in this regime of very low wind speed, which is in the ICC, where you're sitting in an area of larger scale divergence, so it's quite suppressed. Nothing moves. There's also not so much convection there. Um, I mean, that layer will be shallower. The question is indeed if the convection goes as deep as the sort of mixed layer, or whether it's really has collapsed down to something that's really quite shallow. Um, so there, I don't know. It looks like it's actually decoupled from higher levels. Yeah.
And in those cases, can you use the surface values as the integrated property value for that budget? No.
I'm guessing not, because the winds are so different at the surface and aloft. Um, so I'd have to think more of that. I know that's probably not an entirely satisfying answer. I was wondering a little bit for the ocean community is whether this momentum budget is something that you can equivalently do in the ocean if you would have ADCPs, or if you would measure your currents or in your turbulence. If there's something where you can think of an experiment where you also try to constrain that on the ocean side of things and integrate over to see what's the integrated stress that the ocean gets. I'm not sure if someone has done that, or that's a question I have. Yeah. Anyway, if someone has thoughts on that, I'd be happy to hear.
I'm sure people do have thoughts on that, but
Yeah.
Leah Siegelman has her hand up, so
Right.
go to that first.
Great. Yeah, thanks for the talk. I thought it was really interesting. I had one question regarding the work you showed that you did with Chris Chapman of the scale
Yeah.
of tau. And I was wondering, do you think the fact that you've identified scales between 2.5 and 20 as non-relevant or non-contributing, do you think it can be correlated with ocean mesoscale SST variance because you're in this region of relatively
Yeah.
and so, yeah, I was wondering.
Well, Chris, are you here? I see you're here. Do you want to answer that?
I'm here, but it's currently pushing 1 a.m., so I'm not sure if this will be entirely coherent. I think there might be a slight misinterpretation. Those scales between 2 and 20 kilometers were actually the most
They were
dominant.
the
So what
most
Louise
dominant.
was
Yeah.
showing there was the what's left. So if you imagine that you've got a model like Icon or something like that, and you pass that to your bulk flux, Icon's running at 1 to 2 kilometers. So we're in what we call cloud resolving universe, but not necessarily resolving down to the scale that the LES does. We pass that to the bulk flux, the bulk formula, and we obtain something that looks pretty much like what we have when we have the fully resolved domain. Then we filter and we pretend we have only something like error 5. We pass that to bulk flux, and we extract something that's quite smoothed compared to what we see from the fully resolved simulation. So it's in that two-ish kilometer to 20 kilometer, I think the real action is happening. And that's when you look at the formation of cold pools or convective rolls or something like that. Those are the scales that are showing up once the system has begun to organize. Does that make any sense at all? I'm not sure if I was particularly coherent.
Thanks a lot for clarifying. That makes sense. So do you see signature of the underlying ocean in tau?
In this case, the SST has a journal cycle, but the SST is homogeneous across the domain. So in this case, the ocean cannot have any imprint. So that's another, I think, important message is that the atmosphere can create lots of variability in wind and wind stress, especially when there's a very lively moist convection above, which doesn't have anything to do with what the ocean underneath is doing. So if you're asking whether those smaller scale SSTs have an influence on wind, even in this regime, Shanyu Shen has worked on that. She tried to really look at little SST patches and look at wind. And she has also done large eddy simulations, putting in an SST patch and studying the response. It's much, much weaker than you'll find over, mid-latitudes, boundary currents, because the convection is so lively and it messes the signal up. So they really have to do a lot of compositing to see that, also here, if you have a warmer SST, you'll start to drive a somewhat deeper mixed layer, but it's really subtle, much more subtle than I think the action that the atmosphere is putting on.
Okay, cool. Thanks so much.
Thank you. We are just about at the top of the hour. Anish Subramanian ran away to teach, but he left a question in the chat, which he's hoping to get out of the recording. So I'll quickly read it. He asks, I was curious about how different regimes in the planetary boundary layer, stable versus different levels of instability, would impact the momentum flux in this framework. For instance, there's recent work showing that within atmospheric river environments with strong winds at the top of the boundary layer, we see warm, moist air over a cold ocean that stabilizes the boundary layer despite having different convective regimes.
Right, so it stabilizes the bone. I'm not sure what he means with then having a different convective regime. I'm
maybe leave that part off. Warm, moist air stabilizes the boundary layer.
Right, and I mean, then of course the winds will look more like stable boundary layers, and you'll have a much shallower layer over which you're mixing. And so also, your momentum fluxes will be confined to shallower layers.
Mhm.
And yeah. Right. So indeed, in different PBL regime, depending on your stability, but there's, and I think that's something to be careful about. There's the stability in the surface layer, which is very relevant, I guess, for the small scale turbulence. And then the atmosphere will care a little bit more about the stability throughout the rest of the boundary layer. But in fact, if you have very strong wind speeds and convection is organized and it's producing precipitation and cold pools, it doesn't hold any relationship anymore with surface layer stability. In the way where you think, oh, it's more unstable or it's stable. Now this means something to what stresses you can introduce. No, the atmosphere has its own dynamic and no longer really cares about that. I think only at the very low wind speeds is where that stability really starts to become more important. Yeah. But I will write to him.
Yeah, so we should wrap up now since we're at the end of the hour and people will have to run away. Thank you for a really stimulating and wonderful talk. I'm sure people will have lots to follow up on separately too.
Great. Thank you again. And yeah, have a good day and talk to you soon.
So for